A coffee machine control board that powers on and completes one brew cycle may still be unfit for a controlled pilot. A successful sample can conceal unstable firmware, undocumented rework, component fit problems, an evolving bill of materials, or a test procedure that different operators interpret differently. The real pilot decision is whether a bounded design can be assembled, tested, recorded, and reviewed consistently across multiple units. A prototype is primarily a learning instrument. It establishes whether the schematic, firmware, temperature sensing, pump logic, heating behavior, connectors, and enclosure assumptions can work together under observed conditions. A controlled pilot has a different purpose: to generate reliable evidence about repeatability. Remaining uncertainty does not need to disappear, but it must be visible, limited, and suitable for investigation during a defined build. The first gate is design and firmware stability. The schematic, layout, bill of materials, assembly drawing, programming file, and test instructions must all identify the same build. Firmware needs a named version, defined expected behavior, known exceptions, a programming method, and a rollback route. Informal changes between units destroy comparability because the team can no longer separate assembly variation from software changes, alternate components, or undocumented design corrections. Change control is therefore part of the test method. Each board should be linked to its hardware revision, firmware revision, component configuration, observations, and final disposition. Teams must also decide which changes require affected tests to be repeated or the pilot to restart. A label correction may only need documentation, while a different sensor, firmware threshold, relay configuration, or heater control rule may invalidate earlier evidence. The second gate is system-level control verification. Bench behavior alone is insufficient because heating, pumping, temperature measurement, relay switching, user inputs, indicators, and fault responses interact inside the appliance. Test conditions, safe boundaries, observation methods, and pass-or-fail criteria must be explicit. The temperature control path should use the relevant sensor type, placement, calibration approach, and fault states. NTC behavior can be influenced by contact quality, thermal mass, placement, and firmware filtering. Relay evaluation must use the intended loads and timing conditions. Hearing a relay click does not establish correct switching behavior. Pump operation should be assessed within the application sequence, where flow, heat, timing, and user interaction affect the result. Sensor disconnects, implausible readings, delayed heating, unexpected switching, and interrupted pump sequences all require defined responses. The third gate is manufacturing repeatability. Component availability, placement data, assembly instructions, soldering profile, inspection scope, programming steps, and functional testing must be sufficiently defined for the limited run. Design for manufacturability feedback can expose placement, clearance, panelization, solderability, and access concerns. Design for test review can clarify test points, programming access, fixture assumptions, and observable signals. Inspection and functional testing provide different evidence. Visual inspection, or AOI, can identify assembly concerns, but neither demonstrates complete appliance behavior. Conversely, a functional pass does not erase poor assembly records or unexplained rework. Both evidence types must be retained without treating them as interchangeable. The final gate is the controlled readiness decision. 6 records make that decision interpretable: the design release, firmware release, system test record, material readiness record, assembly process record, and learning loop record. Unknown revisions, unstable firmware, or undefined heater testing are blockers. Material or process limitations may remain open only when their impact is understood, contained, and approved. Every board or lot needs a unique identifier connected to its revisions, programming, and component configuration. Deviations, failures, suspected causes, containment actions, owners, and next build decisions must be logged. Authority for substitutions, rework, firmware updates, and test changes should be assigned before assembly begins. Public specifications for a board such as Vortixion's Coffee Maker PCB board can establish an initial manufacturing and control board context. They cannot prove compatibility, appliance-level validation, certification, delivery, or readiness for a particular production decision. That judgment must rest on project-specific evidence. A pilot is ready when it can produce controlled learning rather than isolated success. The outcome is not merely go or no-go. It identifies what supports continuation, which risks are contained, and what must be resolved before a wider production commitment.